turn on this mic. Yes. Hello, everyone. Sorry. Hello, everyone. My name is Chang-Wan, and a PhD student at the Ohio State University. Today, I'm going to talk about GPU code optimization using abstract kernel emulation and sensitivity analysis. Here is the overview of our work. The goal is to optimize code. We identify and relieve performance bottlenecks. So we introduce SAKE, sensitivity analysis via abstract kernel emulation to identify performance bottlenecks. In SAKE, performance modeling is done by fast abstract kernel emulation to expect execution time, and multiple abstract kernel emulations with different hardware parameters are used to identify performance bottlenecks. As you can see, the input of SAKE is a binary code, and the output of SAKE is informations of performance bottlenecks, and those informations are utilized in two contexts. The first one is automatic code optimization, and the second one is manual code optimization. As you know, on GPUs, there are various kinds of resources, but performance is typically limited by one or more resources. So to optimize code, we have to identify and elevate performance bottlenecks. So there are two resources. The first one is the latency of bottleneck, latency of resource, and the second one is throughput of resources. In the first scenario, the only way to improve performance is increasing concurrency. For example, if performance is bounded by global memory latency, then we can increase warp level parallelism, I mean the number of active threads, or we can increase instruction level parallelism with respect to global memory operations. On the other hand, if performance is limited by a throughput, then increasing concurrency may not be helpful because the bottleneck resource is already saturated. In this case, the only way to improve performance is decreasing the number of instructions with respect to that resource. For example, if performance is limited by global memory throughput, then we can reduce the data volume of data accesses by reusing data in caches or registers. So abstract kernel emulation is a simple performance model with respect to each hardware resource characterized by a set of micro benchmarks. And once based on that, abstract kernel emulation mimics actual scheduling of instructions without actual execution based on modeling for resource availability, which is associated to throughput, and instruction dependency, which is related to latency. Also, to enhance the speed of abstract kernel emulation, we only emulated a maximum set of thread blocks that can be concurrently launched on one SM, streaming multiprocessors. So as you can see, once latency and throughput of each resource is obtained by offline micro benchmark for a target platform, then abstract kernel emulation can predict execution time by analyzing the binary. So let me explain two parameters of abstract kernel emulation. The first one is latency, which is the total time for a request to be completed by a resource from start to finish. And the second one is II, initialization interval, which is actually some inverse of throughput and can be defined as the minimum number of cycles between the start of execution of two successive requests to the same resource. Conceptually, each resource has unbounded length of queue, and each resource can admit a request for every II cycles, and after that resource is admitted, it can be finished after latency cycles. So here is an example of abstract kernel emulation. As you can see, there are 3 instructions, and S1 and S2 are memory instructions, whereas S3 is functional unit instructions. And there is a dependency between S1 and S3, and the number of WAPs are constrained to 1 for simplicity, but in the actual abstract kernel emulation, multiple WAPs can be launched concurrently by employing a WAP scheduler. Also, global memory latency is assumed to be 100, II is 20, and functional unit latency is 30, and functional unit II is 10. As you can see, S1 is not dependent on any instructions, so S1 can be executed at time step 0, and it can be finished at time step 100 because global memory latency is 100. After that, resource available time is increased by each II, which is 20. Similarly, S2 is not dependent on any instructions, so S2 can be executed at the resource available time of global memory, which is 20, and it can be finished at 120 because of this latency. For S3, as I mentioned, this instruction is dependent on S1, which means S3 cannot be executed until S1 is finished, which is time step 100. So S3 can be executed at time step 100 and finish it at 130 because the latency of functional unit is 30, and resource available time is increased to 100, which is 100 plus 10. Because at time step 100, functional unit resource is admitted, so the final time is 110. Now, we can identify performance bottleneck by launching multiple abstract kernel emulations with different hardware parameters. For example, if we want to know where global memory bandwidth is a bottleneck or not, then we can do 2 abstract kernel emulations. For the first abstract kernel emulation, we use the original global memory bandwidth, which is assumed to be 400 gigabytes per second. And in the second one, we change the global memory bandwidth by 10%, which is 440 gigabytes per second. If 2 predicted times are very similar, then this code would be not sensitive to global memory bandwidth. But if predict time is changed almost to 10%, then this code is very sensitive to global memory bandwidth, which means this code is global memory bandwidth bottleneck. Here are some of the details of abstract kernel emulation. Full details are available in the paper. As I mentioned, latency and II are modeled, and greedy and oldest scheduling is used. And to enhance accuracy, we consider some additional factors such as barrier synchronization, conditional branches, uncorrelated memory accesses. Some of the aspects such as dynamic data dependent branches or cache effect has not been modeled. Definitely, if we model those effects, the accuracy of abstract kernel emulation can be further enhanced, but the ultimate goal of our work is not on developing an accurate model, but on developing a sufficiently accurate model to guide auto-tuning and manual optimization. Also, I will show how abstract kernel emulation can be incorporated with cache hit rate a little bit later. To evaluate prediction accuracy, we used all the 89 kernels in the Rodinia benchmark suite, and in the paper, we used 2 machines, but here we only present result on Titan X, which is Pascal machine. As you can see, each point of x-axis is a benchmark of Rodinia benchmark suite, and y-axis is a prediction error. The close to the green line, the better. As you can see, for majority of benchmarks, prediction errors are between minus 30% to 30%. We observe that this error is enough to guide auto-tuning. Actually, performance can be significantly affected by cache, so we incorporated abstract kernel emulation with cache hit rate, which can be obtained by MV proof, which is a profiler at NVIDIA. Some details are covered in the paper, but as you can see, red dots, in many cases, prediction errors are further reduced. Now, let me explain how Sake can be used in automatic code optimization. In automatic code optimizations, we considered configuration space as grid reshaping, thread block coarsening, or loop unrolling. This configuration space can be used, for example, for a tensor contraction code has about 66,000 configurations. So the strategy to find a good configuration with a short time is very important. So goal of our heuristic model-driven search is finding a good configuration with a very short time. And key idea behind this search is to start from an initial configuration and iteratively move along the canonical search space by either doing grid reshaping, thread block coarsening, or unrolling until termination condition is reached. Also, model-driven search iteratively seeks to relieve the most significant GPU bottleneck resource like gradient descent search. The model-driven search can be also incorporated with OpenTuner, which is an auto-tuning system using ensemble search techniques, and it allows the inclusion of customized search techniques. As you can see, what we did is we passed the best parameter obtained by model-driven search to OpenTuner as the initial seed. So there would be three different strategies. The first strategy is pure model-driven search. It would be fast, but it may not reach the best configuration. The strategy 2 is auto-tuning with model-driven seed, which is I explained. And strategy 3 is pure auto-tuning. I mean standard auto-tuning without providing seed from model-driven search. So we evaluate performance speed up with respect to the base configuration with each strategy. But as you can see, strategy 2 and 3 produce the same result. So we only present two bars. We use the same Rodinia benchmark, and the blue bar is performance speed up with OpenTuner, and green bar is performance speed up with model-driven search. As you can see, model-driven search, which is the best configuration or close to the best configuration, which significantly reduced auto-tuning search time. Also, as I mentioned, strategy 2 and 3 produce the same result. So the issue is the time for finding the best configuration. So we compared time with two strategies. This curve is the ratio of tuning time with only OpenTuner to tuning time with model-driven search plus OpenTuner. As you can see, tuning time is significantly improved when model-driven search is incorporated. The reason is when model-driven search is incorporated, OpenTuner can start with a very good configuration. Now, I'm going to explain how Sake can be used in manual code optimization. This is a tensor contraction code generated by the tensor code generator from the production NWChem computational chemistry software suite. and we split the entire code into 4 code regions. And in code region 1, base index is computed by special function unit. In code region 2, partial inputs are brought from global memory to shared memory. And in code region 3, partial results are accumulated in registers using shared memory. And code region 4, output is written out from registers to global memory. As you can see, the initial performance is only 92 gigaflops, but we iteratively identifying and relieving performance bottlenecks, so final gigaflops are 161 gigaflops. Let me show you how. Actually, we did sensitive analysis with respect to each latency and throughput, but as you can see, the bottom left table, we only shows sensitivities with respect to global memory latency, special function unit latency, and global memory throughput, because they are mostly sensitive to performance. And the 4 columns, except for the first column, present the region-wide sensitivity for code region 1, 2, 3, and 4. And each percent is the sensitivity with respect to the total time, not time taken in each code region. As you can see, the most sensitive part is global memory throughput in code region 4, which is 52%, which means this performance is mainly suffered from global memory throughput in code region 4. So the reason is there are 2 memory operations in code region 2 and code region 4, and they read in a complementary way of mapping. So memory accesses in code region 2 is call list, but memory accesses in code region 4 are on call list. So by flipping the mapping, we can make memory accesses in code region 2 on call list and memory accesses in code region 4 call list. I mean, by this transformation, we can reduce data volume in code region 4, but we can increase the data volume in code region 2. This would be beneficial because, as you can see, the sensitivity with respect to global memory throughput in code region 2, which is only 6%, if we allow more memory instructions in code region 2, performance may not be degraded much. So after this transformation, performance is improved from 92 gigaflops to 123 gigaflops. Now we can focus on special function unit latency in code region 1. Similarly, the sensitivity with respect to global memory throughput in code region 1 is 0%. So we can allow some more global memory operations in code region 1. So what we did is we pre-computed these indexes and put them in global memory. So these long latency special function unit operations are converted to memory access operations. So performance is improved to 139 gigaflops. Now, the most sensitive part is global memory latency in code region 4, which is 40%. We figured out the instruction level parallelism in code region 4 with respect to memory accesses are very low. So we reordered instructions to increase ILP in code region 4. So sensitivity in code region 4 is decreased from 40% to 10%. At the same time, performance is improved to 161 gigaflops. Now, the most significant part is global memory throughput in code region 4, which is 39%, but we cannot reduce data volume in code region 4 because this data volume is related to accessing the output matrix, which is constant. Let me summarize our work. Code optimization and transformation can be guided by identifying bottleneck and relieving bottleneck. So we developed the Sake, which is tool for identifying performance bottleneck. So Sake can be utilized in two ways. The first one is automatic code optimization, where we will show incorporating our model-driven search with Autotuner can enhance performance. In manual code optimization section, we can split the code into many regions. Then we can find the bottleneck in code region and iterative improve performance. And finally, I appreciate Professor Sadapan, Rinwell, and Jay Ram and Mahesh at NVIDIA for improving slide. Thank you.
So we have time for a few questions, and for questions because of the recording, please use the microphone if you have any. All right, so I actually had something to ask you, which is looking at the kernels that you were using. You were showing things like instruction dependencies and things like that.
You mean slide in abstract kernel emulation?
Yeah, that's right. So that, and I wondered that in the title of your talk, you talked about GPUs. This looks similar to what one would use for doing performance evaluation of scoreboarded CPU architecture as well. I was wondering, could you comment on how this is, if this is specific to GPUs, and if so, how?
You mean if this strategy is applied to some architecture, then what happens? Is it your question?
Yes. Well, the title of your talk says GPU, so I was just wondering, how is this, or is this specific to GPUs?
I think that is a very good question. And actually, I think this strategy about some identifying and relieving performance bottleneck can be applied to all architectures and platforms. So I think this strategy can be applied to CPU architectures. But you know, in CPU, pre-fetching can significantly affect performance, where a GPU doesn't. I mean, in GPU, pre-fetching is not exist. So I think we need some modifications to apply this model to CPUs. Thank you.
Yes, I have a similar question. So, a good talk. Congratulations. I want to understand how sensitive your technique is to the performance stability, like predictability of the architecture. Because GPUs, they are very predictable compared to out-of-order CPUs. So, how sensitive are your results, you think, to the fact that the architecture is timing predictable?
Yeah, actually, I think there is a trade-off between some accuracy and efficiency. So, I mean, there are many architectures having different characteristics, right? So, I think for some architectures, this simple model is not applied. So, for those architectures, we have to consider some additional factors. I think that is the key in the paper.
Okay, maybe we can make this the last question.
Hi, this is Bontinho from Rutgers University. I have a similar question: is how you can make sure your performance prediction is accurate? Because we know it depends on your application pattern, maybe compute bound, maybe memory bound, and also depend on the architecture, the type of GPU core. So how you can make sure your performance prediction is very accurate?
Is your question is how can I make sure this prediction is accurate?
Yes.
Okay. This tool is not fully automated. So like some loop count is manually counted, but we consider some branch or some uncorrelated memory accesses, and they are automatically considered. So if we count some loop, if we consider loop counts correctly, I think this result would be fine.
Okay. Thanks.
Thank you.
Okay, shall we thank the speaker again?